the measure, Jordan and Lebesgue measure, when we apply some differentiable mapping. And let me start with very simple examples of mappings. So, first definition, translation of a set. Okay, I forget the notation. Yeah. A in the direction y, which is denoted is the set T y of A equals to the set of axes such that x can be represented as x tilde plus y, where x tilde vector belongs to A. And also dilation of a set A with respect to y with coefficient, with dilation coefficient alpha belongs to, let's say, 0, 1, get a 1 plus infinity, is the set, oh, I forget about notation, but it will be here now, alpha y of A equals to the set of all x's such that x equals to y plus alpha x tilde, where x tilde is in A. So translation is if we have a set like that, right? That is A, and we have a vector y, then the translation is this set. Okay, very good. Yeah. Yeah, that is translation to vector y, and dilation is, so we have y, vector y, we have somewhere here, let's say, the set A, and so if alpha is, let's say, 2, then everything is increased in 2 times, so this will be something like that. Yeah, that is 2y of A. Okay, these are transforms which can be easily understood from the point of view of the measure. So let me write like that. Since measure doesn't matter Jordan or Lebesgue, of a translation is equal to measure of A, and Lebesgue or Jordan measure again doesn't matter of dilation equals to alpha to the power n measure Jordan or Lebesgue of A for arbitrary elementary set A in Rn and Y in Rn, then the same relations hold for any Jordan or Lebesgue measurable sets A in Rn. So once we have a measurable set, we can approximate it by elementary sets, and for elementary sets obviously we have this property just by looking at what happens with intervals in Rn, right? Okay. So what is more important is that it is possible to prove, and in fact it will follow from properties of the integral, of the multiple integral. So it will be considered in the next semester. But for a while, let me only mention that, in fact, for any motion of the space Rn, the Lebesgue measure of a set does not change. So let me recall what is motion in a space. In fact, there is a classification of motions. For example, for the plane, what are motions? Rotations, translations, symmetries, and compositions of those things. For the space, it's a little bit more complicated. Also, I don't know what is precise English term for this rotation with slicing. I'm not sure. and not important. So I don't want to go deeply inside motions of the space or the plane, doesn't matter. The point is that the Lebesgue measure does not change. That's important. And in fact, it turns out for a long time there was a problem. Okay, so you see, I gave you an example of a set which is not measurable in Lebesgue sense, right? So then you can say, okay, maybe Lebesgue was not very good, and it is possible to create some other notation of the measure, right? Because we studied Jordan measure, Lebesgue measure. But it turned out that if you will try to find some way to measure sets in Rn, right, in such a way that the property of sigma additivity, remember what is sigma additivity? Measure of disjoint union, right? Like that, of measurable sets is equal to the sum of measures. Disjoint union, right? So union when all sets do not intersect each other, right? So that is sigma additivity. So once you have this property and also that property, that Lebesgue, that measure should be preserved when you apply a motion, right? Of course, once again, that is very natural property, right? If you have a motion, then measure should be preserved, right? And it turned out that if you want to have a measure such that you can measure every set, right? Every possible set in Rn, and invariance with respect to the motion, right? Also that property, and of course, let's say measure of empty set is 0, measure of the whole space is infinity, then no way to solve that problem. And in fact, the proof is precisely the same like we did for the example of non-measurable set. So once you have measure of a point should be 0, otherwise it's impossible, right, to measure anything, because if you have infinitely many points, then measure will be infinity, right? So everything will be infinite. Oh, but in fact, indeed, that is a way to measure everything, by the way. Yeah, so I should exclude it. Measure of a bounded set should be not infinity, right? Otherwise, you can accept let measure of every point would be 1, let's say, right? Then everything is okay. Every infinite set has measure infinity, and of course all properties are satisfied. That is not very good, definitely. And so then next question was, okay, we cannot obtain anything very good with this property. Let us change a little bit. Only finite additivity. Then it turns out everything depends the dimension. Banach proved that for n equals to 1 and n equals to 2, there are infinitely many measures which satisfy all properties of measures for every set. And you can measure every set by those measures. But you see only finite additivity, no sigma additivity. And sigma additivity is a very natural property, in fact. But for n greater than 2, Hausdorff proved it's impossible. Both results are sufficiently difficult, but I wanted just to mention this possibility. Okay, now we can, not yet. I should also make another definition. A mapping F from a set G to D, G in Rn, D in Rn, is called a diffeomorphism if it is continuously differentiable its Jacobian is never 0, doesn't vanish. Let me use this. Doesn't vanish in G. Continuously differentiable in G. Yeah, in G. And f of G equals to D, and there is inverse mapping f minus 1 from D to G, which is also continuously differentiable. In D. And obviously translations and dilations are examples of diffeomorphisms, because both are differentiable. In fact, derivatives are, so for translations, derivatives are, look, unit matrices, right? And of course, inverse mapping is also a translation. And dilation has Jacobian matrix diagonal with alphas on the main diagonal. So indeed, those are elementary examples of diffeomorphisms. Next is an agreement. Okay, what is... Yeah. If we talk about a diffeomorphism f on, okay, now let's be on D, because mapping doesn't matter. On D, then we'll suppose okay, let it be bound, only bounded set, a bounded set D. Then we'll suppose F is a diffeomorphism diffeomorphism on an open set G, which contains closure of D. And then I plan to use a theorem, better to say not theorem, but the method of Theorem 1, image of a cube of smaller dimension. We'll use the method of the proof of that theorem. And look, I'll use the following observation also. Look, so we have this agreement. So we have somewhere our set D, right? That is D. Then the closure of D, let it be the same picture, closure of D is bounded, so closure of D is a compact set. Why? Because it is bounded and closed. Bounded because of boundedness of D, and closed because this is closure, right? So that is a compact set. Then this compact set is a subset of open set, right? Hence, for arbitrary point x in closure of D, there exists epsilon x, let's say, such that neighborhood with this radius of x is in G. That is because G is open. So every point of G is inner point. Then the union for all x in closure of D of those neighborhoods obviously covers our closure of D, right? Because you see, every point belongs to the ball with center at that point, right? Union, so we have open covering of this compact set. By the definition of compact, so because of compact, what we can do? We can find finite subcovariance. So there exist finitely many points, x1, so on, xn, such that union of I from 1 up to capital N epsilon xi of xi's still covers our D. And simultaneously, each of them is in G, right? And in fact, what we can do? In fact, we can, yeah, I can use here, let's say, epsilon x over 2. Yeah, over 2. And here, epsilon xi over 2. These are still covered, right? And then what we obtain? Then we have finitely many balls, right? Finitely many balls, which covers our set completely, right? And moreover, if we'll consider closure of those balls, then, because here I took epsilon x over 2, and I have a property that even with radius twice more, that is still in G, right? Then closure of this union is, so closure of this union is still in G, right? Still in G. Of course, that is a bounded set, so why it is bounded? We have finitely many balls, right? Union of finitely many balls. That is a bounded set. So that is a compact, right? That is a compact. And then what we can do, we suppose F is a diffeomorphism, right? On G. Hence, it is diffeomorphism on this compact set. So then we'll consider in the future, so you see, it means I had our set D, and now I can enlarge it a little bit. And I describe now how we can enlarge it. So the process of this enlargement allows us to enlarge a little bit, right? And still, you see, on this enlargement, our diffeomorphism is still a diffeomorphism. Hence, we can consider maximum of the norm of derivative. What is necessary to use the method of the proof of Theorem 1? If you remember, let me recall. Okay. Okay, I think now I can okay, let me denote this closure. Let me denote it by D extended, like that, extended. D extended. So we enlarge it a little bit. D extended. Okay, now I can formulate Theorem 2. So Theorem 2 says that if D is a bounded Lebesgue measurable set and F is a diffeomorphism on D, C agreement, right? Then F of D is Lebesgue measurable. In fact, the same result is true for Jordan measure. So also diffeomorphisms, they preserve Jordan measurability as well. But I'll prove here only Lebesgue. Proof. So first of all, let us study what happens with elementary set and even what happens with an interval. So let P be an interval in Rn. So recall what it means. P equals to product of some intervals, and brackets mean that we can either include or exclude the end of an interval, right? Then we can observe that P is a subset of the interior of P, right? Together with just equals to together with P intersected with the boundary. Now, like that. Let me write like that. So, in picture, if I have a part is included, right? So what is this? That is the interval in R2. So the interior plus the intersection of P with the boundary, right? So here it consists of three line intervals, right? Then mu, in fact, even Jordan measure of P intersected with dP. Okay, here I put outer measure. That is because I don't know yet what is it. And that is less or equal than outer measure of the whole boundary. And now look, what is boundary of the interval? What is boundary of the interval? It consists of finitely many intervals of smaller dimension, right? But, oh, sorry, I forget to insert F. F of that. F of that. F of that. And remember So boundary contains finitely many cubes, not cubes, intervals, or intervals of smaller dimension, right? We proved that diffeomorphic image of a cube is 0, right? Has zero measure, smaller dimension, right? And of course, same is true not only for cube but also for any interval. The proof practically doesn't change. Hence, that is 0, right? That is 0. Yeah, so so you see, it means that hence the even Jordan measure, and hence also the Lebesgue measure of the image of the boundary is 0. But now what is about f of interior? Of course, I should suppose that P is in, at least in this open set, right? In this open set. Otherwise, makes no sense because no f. Then we know that, so if you see f is diffeomorphism, means that its Jacobian is never 0, right? If Jacobian is not 0, so look at arbitrary point here in this interior. That is interior point, right? So there exists a neighborhood such that in this neighborhood our f is 1 to 1, and we can apply, in fact, inverse mapping theorem. And according to inverse mapping theorem, you can obtain 1-to-1 correspondence between a neighborhood of point here and a neighborhood of the point in the image, right? And then if you have 1-to-1 correspondence, then it means that arbitrary point in the image is also an inner point. Because look, you have, so okay, P is in fact like that, right? So you have here a point. This is an inner point, right? So then you can map it. Okay, I don't know what is this f of P, right? F of interior, sorry. F of interior. And what we know by the inverse mapping theorem, you have 1-to-1 correspondence between this neighborhood and neighborhood of the image here. 1-to-1 correspondence, right? So this neighborhood should be in this image, right? And since arbitrary point here is obtained as an image of a point from this interior, right? We obtain that arbitrary point here is an inner point. So that is open set. And hence it is Lebesgue measurable. So you see, what is the image of P? That is f of this open set, Lebesgue measurable. F of this has even Jordan measure 0. So altogether we have measurable set. So for arbitrary interval, the image of this interval is a Lebesgue measurable set. Okay, then what we have? So now we know that for an arbitrary elementary set M in fact even in G f of M is Lebesgue measurable. Lebesgue measurable. Okay, then why? Because elementary set consists of finitely many intervals. Each image of each interval is a measurable, hence finite union also is Lebesgue measurable. Next, next observation is as follows. So f of the interior is an open set in Rn. Hence, we have a theorem about structure of open sets in Rn. Hence, it can be represented as a disjoint union. Now remember I used disjoint union like that. Yeah, I used this disjoint union of countably many G. Okay, let it be GK. Countably many elementary sets. Elementary. So every open set can be represented as a union of countably many elementary sets. Measure is finite because everything was bounded. Hence, yeah. So measure of this is equal to the sum of measures. Oops, K. Let it be K. K from 1 up to infinity. Measure of GK. Here we could write volumes, but doesn't matter. So the series converges. The series converges. Hence, converges because it has finite sum. Hence, for arbitrary epsilon greater than 0, there exists, let's say, capital K, such that the sum K starts from capital K up to infinity of measure of GK is less than epsilon. Then what we have? Then the union, let me denote M epsilon, let it be the union of the first K small from 1 up to capital K of GK. That is elementary set, because we have union of finitely many elementary sets. That is elementary. Elementary. And also because union of all of them was equal to that. Now we considered part of that union. So that is a part of our image of the interior of M, right? And what we have? We have that measure of this interior minus measure of volume, doesn't matter, of this elementary set. That is precisely this sum, which is less than epsilon. So that is a property of elementary set. So you see that for an arbitrary elementary set, and of course, oh, by the way, I can't forget about interior here. Why? Because as we saw, f of interior and f of the whole, they differ by measure 0. So I can put here just f of m. And also here also that is a part of f of m. So you see, for an arbitrary elementary set M, we can find, for an arbitrary elementary set M, we can find an elementary set M epsilon such that this M epsilon is a subset of the image of this image of this M, right? Image of this M. So elementary set is a subset of the image of M, and the difference between measures is less than epsilon. Okay, now I want to use also the following property. Practically, we proved it during Theorem 1. So for arbitrary set E, doesn't matter measurable or not. Okay, let it be in G, not G, what was dx extension. We can write the estimate for the outer measure of the image of E, and it is less or equal. So let me recall in Theorem 1. So what we did in Theorem 1, in the proof of Theorem 1. I had small cube, right? Small cube. And we observed, let me cite this inequality. Yeah, it was like that. Let me cite this inequality. Maximum of x, y in k delta L, f of x minus f of y less or equal m square root of mn delta, and we deduced that that I didn't write this inequality. So in Theorem 1 we had different dimensions, right? Different dimensions. But now I want to use same dimension, right? And also remember that after that there was, in fact, there was a boundary for the outer measure of the image of the whole cube, right? But I want now to use, so it was like that. It was like n to the power n. Once again, it was in the proof. 2m square root of mn delta power m, right? This was the estimate. And now look, instead of cube ki, I can consider arbitrary set. Arbitrary set. And what we need to change? So this was number of cubes, small cubes, right? So I don't need to put it. And this was precisely the distance between, estimate for the maximal distance between x and y. Yeah, so it means that I can estimate analogously. So now m equals to n, and it gives 2m n to the power n of times, outer measure of E. So by similar consideration. So instead of cube, now we consider arbitrary set, and we estimate the distance between arbitrary points of this set. And yeah, in fact, yeah, what is capital M? Capital M is maximum f prime at xi for xi in this dx. Yeah, that is the estimate. And now, yeah, so delta to the power m was precisely the measure of this small cube. So I replace it by outer measure of E. And that is the estimate. Yeah. Now I can proceed further in the proof. So now we come to our bounded Lebesgue measurable set D, right? So D is Lebesgue measurable. D is Lebesgue measurable set. Hence, what we know that for arbitrary epsilon greater than 0, there exists maybe not epsilon, maybe delta should be here. No, now epsilon. There exists an epsilon, that is elementary set, elementary, such that the Lebesgue measure of the symmetric difference between D and n epsilon is smaller than epsilon. Yeah. Okay. Now look. We can suppose and epsilon is in dx. So that is because of C, what I considered here. Dx is some extension, right? And you see, it is formed by countably many balls which contain our set D. And once we have a part of this, an epsilon, outside of this, right? Then what we can do? Okay, part is outside, but other part is in the ball, right? So I can, roughly speaking, consider smaller part of our elementary set, which is inside ball, right? So roughly speaking, I can forget about parts of our elementary set which are outside of those balls. Of course, you can say, oh, but if you will look carefully at those finitely many balls and so on, you should write down everything. It's crazy, of course. But just, you see, some geometric intuition says it can be done, right? And I refer to that geometric intuition without going into details. So I can suppose this, and after that I can consider. So hence I can write mu of the image of this now outer measure, of course, because I don't know if it is measurable or not. It will be less or equal than what? Epsilon times this constant, 2mn power n. Okay? Yeah. Okay. And you see that what is this image of the symmetric difference? Remember, F is diffeomorphism. Diffeomorphism has an inverse, hence it is 1 to 1. Because if you have an inverse, then it is 1 to 1, right? If F is 1 to 1, then you can write that is as a symmetric difference between those two sets, right? Now I refer to this observation, which was given for an arbitrary elementary set, right? But now I want to apply this observation to our set capital N epsilon, right? So by the observation, of course, I don't want to use epsilon once again, right? Because epsilon now was fixed. Arbitrary, but it was fixed, it was chosen, right? So I'll apply this observation, but instead of epsilon, I'll take delta. So there exists for arbitrary delta positive, there exists elementary set. How I denote it? Just m delta. There exists elementary set m delta, elementary set m delta, which is in our image f of n epsilon, right? And such that measure of the image of an epsilon and delta, sorry. An epsilon, yeah, an epsilon, it was an epsilon, yeah. Minus measure of delta less than delta. Okay, okay. Yeah. So, yeah. Now what I want to consider, in fact, I want to look at the approximation of our f of d by this elementary set capital MD. Approximation in the sense of symmetric difference. So, look at such a difference, m delta minus f of d. M delta is a part of f of an epsilon, so I can write f of an epsilon minus f of d. Okay, it's enough for me. And then opposite difference. That is a part. Okay, I want that difference. That difference, of course, that is not true, so I should add something. What I should add? I should add a part of this, which is not in m delta. Yeah. Okay. So, using those two properties, I can write out a measure of the symmetric difference between m delta and f of d. So, symmetric difference is union of those differences, right? So, it is less or equal than outer measure of union of those two, that is symmetric difference, right? F of n epsilon symmetric difference with f of d, right? Plus outer measure of the rest. F of an epsilon minus m delta. But look, this is in fact, yeah, it's here. Look, this symmetric difference is that image of symmetric difference, outer measure, less or equal, so less or equal, epsilon times 2m n power n, first term, and second term, look, here everything is measurable in fact. So that is equal to the difference, because that is a part, less than delta, plus delta. So you see now what we obtain. So for arbitrary epsilon and for arbitrary delta, we can find an elementary set md delta such that outer measure of this m delta elementary set and our set f of d is as small as we want, right? Because epsilon is arbitrarily small and delta is arbitrarily small. So by measurability criteria, we obtain f of d is Lebesgue measurable. That's it. That's it. Okay. We finish the proof of this main property for this section. So you see that diffeomorphism preserves measurable sets.